In this next section, we are going to look at the concavity of a function. And we're going to see that the concavity of the function is related to the second derivative. So we're going to start here with a simple example of a function here. And its concavity here, as you see, as you go down this function, at this part of the function, this function is what we call concave up. So the way that I think of it is it's kind of like a bowl. So if water were, if it were like completed and water were to fall in here, it would catch the water. And then at some point it's changing so that it's concave down. Okay, so here if water went into this, it would just roll down, right? It wouldn't catch the water. So you have concave up, bending upwards, concave down is kind of bending downward. Okay, so let's see how this idea of concavity is related to the second derivative. So if you notice here, if I draw some tangent lines to this function as we go through like this, what you notice about these tangent lines is as we go along the curve, the tangent lines are getting more and more steep. So what we could say is the tangent line, the slope of the tangent lines are increasing. And that's another way of saying that the first derivative is increasing. But then when you get to this point where it's like concave down, right, you get some tangent lines here. And what you see here is the slope of the tangent lines are decreasing, right? So in this concave down part, you get that the first derivative is decreasing. So this concave up part, we could write this. We could write f prime of x is increasing, right? This concave down part, where it's concave down, we would have that f prime of x is decreasing. Okay, so the concavity then is related to whether the first derivative is increasing or decreasing. And if the first derivative is increasing, then it's concave up. And if it's decreasing, then it's concave down. So this is why it's related to the second derivative. Because just like the first derivative tells us when the function is increasing or decreasing. So if you remember that corollary 3, it was a corollary of the mean value theorem. If the first derivative is positive, then the function is increasing. If the first derivative is negative, the function is decreasing. Okay, so just like the first derivative tells us whether the function is increasing or decreasing, the second derivative tells us whether the first derivative is increasing or decreasing. You get the idea? The second derivative kind of does what the first derivative does for the function. And I just want to make sure I say all that very clearly, but let me just write this down then. So we could write concavity and the second derivative. And this is kind of an application of corollary 3 to the first derivative. Okay? So if you remember that corollary 3, the function had to be differentiable, and that derivative, or the derivative then had to exist, right? So what I'm going to say here is let f of x be a function, and we're going to say that is twice differentiable on, some interval AB. Twice differentiable means the first derivative and the second derivative exist. Okay? So let f of x be a function that's twice differentiable. And we got these two cases. And I just want to look at them here to see how it phrases it. So it says, so it's doing it. So this is what it's saying. So if f double prime of x is greater than 0, then the original function f of x is concave up. Okay, so if the second derivative is greater than 0, you could say that the first derivative is increasing, but you could also say when the first derivative is increasing, the original function is going to be concave up. So I'm kind of skipping that middle step. If the second derivative is greater than 0, then the graph is concave up. And then you get if the second derivative is less than 0, then f of x is concave down. Okay, so just like the first derivative tells us some important information about the original function, in particular it tells us when the function is increasing and when it's decreasing, and it also tells us where the minimum and maximum values occur, because that's when it changes from increasing to decreasing. So just like the first derivative tells us some interesting, important information about the graph of f of x, the second derivative tells us some more information. And it's telling us when the graph is like bending upward and bending downward, whether it's concave up or concave down. So the first derivative and the second derivative together tells us a lot about the graph of the original function. And in fact, you can use both of those to analyze the graph or even to graph the original function. Okay? So with this in mind, let's just do a couple examples here. What I want to do is I want to investigate the concavity for some simple functions here. We got x squared, x cubed, sine of x, and then we got this cubic polynomial here. So let me start with f of x equals x squared. So to investigate the concavity, what it's saying is let's look at the second derivative and see when it's positive and when it's negative. Okay, so the first derivative here is 2x, and the second derivative is going to be 2. Notice the second derivative here is a constant, and it's going to always be positive. So what this means is that it's always concave up. Right? And this makes sense because we know the graph. This is a parabola, right? Y equals x squared. And indeed, that is always concave up. Okay? So let's look at f of x equals x cubed. Okay? So f prime of x is going to be 3x squared. Okay, and then f double prime of x, the second derivative, bringing the 2 down, is going to be 6x. Notice that f double prime of x is going to be greater than 0 for x, or let me just write it as an interval, for 0 to infinity, and then f double prime of x is going to be less than 0 for negative infinity to 0. So what this is saying is for all the negative values, this is going to be concave down, and for all the positive values, it's going to be concave up. And this, we know what this function looks like. We have this, y equals x cubed, right? And indeed, for these positive values, it's concave up, and for these negative values, it is concave down. Okay, so this fits with the second derivative, right? So now let me do sine of x here, and then I'll do the, or maybe I'll do the sine of x down here, and then we'll do this last derivative up here. Okay, so let's look at the sine of x. So we'll do f of x is equal to sine of x. So f prime of x is going to equal the cosine of x, and then f double prime of x is going to be equal to the opposite of the sine of x. Okay, now let's graph the second derivative here on 0 to 2 pi. We'll just look at this on 0 to 2 pi. So this is the sine of x. So this is -1, this is 1. And it's the opposite of sine of x. So it's going to start at 0 and go down, and then back up, and then up, and then back down. So notice the second derivative is negative here, right? So f prime of x is less than 0 on this side, and over here f prime of x, or f double prime of x, sorry, f double prime of x is greater than 0 over here. So what this means is this is telling us since the derivative since the second derivative is negative, the graph is going to be concave down. Notice the graph of the second derivative is concave up, but the original function is going to be concave down here, and then it's going to be concave up over here. And so now we can graph the sine of x and see that that is the case. And sure enough, this goes up like this, down like this. So this is y equals negative sine x, and this is y is equal to the sine of x. So this is the original function. Indeed, on that first half it's concave down, on the second half it's concave up. And you can see how it's related to the sine of the second derivative. Okay? And so the second derivative again is telling us what the concavity of the original function looks like. So now, finally, let's end with this one. So we're going to do the derivative to this is 3x squared. This will be minus, bring that down, 6x, and then the 2 goes away. So that's the first derivative. So now let's do the second derivative. Bringing this down, I get 6x. This will be minus 6. Okay, well, let's find when this second derivative is equal to 0. And when I do that, I get that x is equal to 1. Okay, and in fact, then, like if I were to graph this line, this would be a line that would like start at or it would start at -6, right? This would be 1, and it would be like this, right? And so you could see this is the second derivative, y, and I could have put a double prime over here, so I could write y double prime is equal to 6x minus 6. And so we can see that the derivative here at 1, it changes from being negative to positive. So this, the graph would be, the graph of the original function is concave down here, and it's concave up over here. Notice that the second derivative is a line, and so it doesn't have any concavity. And you could see that because the derivative of a line, the second derivative of a line would be 0. It would be not just a constant, but 0. So there's no concavity. But the derivative of the cubic, it's a line, and the second derivative of the cubic is this line, and the second derivative has a negative sign before 1, and so the graph is going to be concave down for everything from negative infinity to 1, and then it has a positive sign greater than 1, and so it's going to have a concavity, it's going to be concave up over here. So let's actually graph this cubic equation and see that in fact this is correct. So x cubed minus 3 minus 3x squared plus 2. Let's do a standard window. Okay, and there you can see our graph. So it looks something like this, the original graph. It kind of goes up here at 2. It goes through at 2. So 1, 2, this is 1. So it's like going up here, and it's kind of going down, and then at some point, well, at 1 it actually crosses. So this is a root, and that's kind of too bad, but that's okay. So it is concave down from negative infinity to 1, and then it's concave up from 1 to infinity. And it looks like here where it changes the concavity is actually where it passes through the axis at the same point. That's kind of unfortunate. Let's see if that's the case. I'm going to hit second value, hit 1, and it looks like yes, it does cross the axis. The reason this is unfortunate is that if you could move this graph up and down and it wouldn't change the second derivative because that's just a constant. So it does not necessarily have to change its concavity where it passes through the axis. This is just a coincidence, okay? But what I wanted to say is that there, at this point here, it does change from being concave down to concave up. And that's actually called an inflection point. That's what we're going to be talking about in the next video, okay? But for now, the concavity is related to the second derivative, and when the second derivative is negative, it's concave down. When the second derivative is positive, then it's concave up.